welcome to Toddcast number 30. So they're kind of zipping along, sort of. Continuing on SN1, SN2, this time going to complicate things. So basically want to look at the same reactions, and instead of trying to decide which is which, going to take one step further. Once we decide which reaction it is, deciding between SN1 or SN2, going to take it one step further and look at the nuances within the reaction. So for instance, if you've seen on the previous video, we mentioned rearrangement as something that can potentially happen with an SN1. And so I want to just briefly mention what rearrangement is. So if you have a carbocation, let's say I have a carbocation that looks like this. I'll put this one coming out. It's not chiral, so it doesn't matter, but just to have three-dimensional accuracy, an H. And then on the next carbon, let's say I have just an H and a CH3 with a carbocation. So this is an sp2 center. It's planar. And because there's only 3 bonds and a plus charge, it's not as stable as it could be. So carbocations, they're highly reactive, but in the brief period of time when they exist between the start of a reaction and the final product of the reaction, so as we pass through intermediate transition states, they are free to move around. So it is far easier, going back to the bench analogy, for someone to move over who's already sitting on the bench, one seat, before somebody can come in and sit down. It's just much faster. So there's a phrase in OChem, and that is intramolecular, within the molecule. Intramolecular reactions are always faster than inter. In other words, it's easier to move one seat over on the same couch than it is to run across the room and sit on the couch. So as a result, before a nucleophile can come in, there is time for things to move over. So there's 3 candidates. This carbocation could move over an H, could move over CH3, or could move over CH3. The electrons here can move over, electrons here can move over, electrons here can move over. So a few things to take into account when it moves over. One, you don't want to move something heavy. Molecules are inherently lazy. So this is 15 grams per mole, 15 grams per mole, 1 gram per mole. So it's far easier for hydrogen to move over because it doesn't take much effort to move that nucleus over compared to the other 2 groups. The second thing is, if this group moved over, so let's say this methyl group moved over, then I'm going to say if this moved over, I'll pseudo-erase it. That plus charge would be gone. This would now rehybridize, but the plus charge would be here, and this new CH3 would be there. The problem with that CH3 moving over is that it's still 1,2, a secondary carbocation. You didn't gain any stability. So moving the heavier one is harder, plus it doesn't gain in stability. So what we're going to have to do for this one to work is we're going to have to move the lightest thing possible and see how that works out. So if this H moves over, and notice I'm taking the electrons from the bond to the atom, meaning the bonding electrons with the H are going to move over, leaving an absence of electrons here. All these electrons are moving over to there. So now what I'm going to get is H3C, the blue one staying where it's at, the red one staying where it's at. This is now my carbocation because it lost the electrons. And over on this carbon, I now have that H. I'm going to put this one in yellow, the one that moved over. And honestly, it could have gone to any spot. There's no specificity for why it's where I put it. And so we went from a secondary carbocation to a tertiary carbocation. We gained in stability. So it is worth it for that H to move over and increase the stability. So anytime we have a carbocation, which is going to occur with an SN1 because the leaving group first leaves, you run the risk of getting rearrangement. So that I can guarantee is going to be a monkey wrench in our crankshaft for a lot of these reactions. So let me go ahead and just repeat. Secondary and tertiary, this is more stable. So you want to rearrange to go to a more stable species. So if it can go to tertiary, great. So secondary, tertiary, or primary, tertiary will be ideal. It's next to impossible to get a primary carbocation, so that's the trick for something else. And then also resonance stabilization helps for carbocations. So we'll get into some of those, but for now, just want to mention the secondary and tertiary because that's what we're going to focus on for today. So I'm going to erase what I have here. We're off to the races on this one. So considering before, so here's my molecule, let's say, and the only thing that could possibly be a leaving group is OH, and OH minus is such a strong base, it's going to be a good nucleophile, which means it's a terrible leaving group. So you're not going to be able to lose it as is. So in order to make this reactive, you're going to have to add an H+. So right now it's secondary, so it could go either way. It's a terrible leaving group, so I don't know what's going to happen. But the conditions are going to dictate everything. If it's polar and protic, that will help it to come off. And more specifically, if it's acidic conditions, so if we have an H+, so note that to make this go, I added an H+ to the solution. Made it acidic conditions, lower the pH. So if I protonate this OH, it goes from an OH leaving group to suddenly water, which is highly stable when it leaves. So this H gets protonated, and those electrons right here, this leaving group, can go like that. When it goes like that, you have water given off, so I'm going to just write my water up here. That's my side product. That's what's been released. And you have a carbocation, which by all accounts is one R group, two R groups, and an H, so it is secondary. Is there a chance to make it form a tertiary? So just like we had before, we can move this H over, but also we could move this H over. So if one of the H's over here moved over, then that would make this one stabilize, but then this one would have an H, carbon, and carbon. It'd just be secondary. We didn't get anything. So in theory, it could just do the entropy, but the one that's going to be productive is the one that forms tertiary. So again, look for hydride shifts first. We call them hydride shifts because the H is moving hydrogen, but it's moving with 2 electrons, so it's hydride. So we're going to refer to this next step as a hydride shift. So can it become more stable? We've got a three-legged carbocation, planar intermediate, and the potential for rearrangement. So when that H moves over, we underwent, again, something called a hydride, H with a negative, shift. Okay, so the rearrangement was an H minus moving over, neutralizing this charge here and creating a plus charge in its wake. So we went from a secondary to a tertiary carbocation. That's not a 30, that's a 3 with a degree, so tertiary. Now it's free to be attacked. So we didn't mention what the nucleophile is, but let's say the nucleophile is a thiol. So once the leaving group's left, the thiol is free to attack, stabilizes that carbon, now that carbon's neutral, but the plus charge has to be included from the time it's first protonated. So H+, plus is now here, plus is now here, plus is now here, plus is moved to the sulfur. This is known as a catalytic proton, meaning it goes on in the beginning, but it has to come off in the end. So if these electrons from that bond to H fall off, the sulfur takes them back, then H+ has been regenerated. So those come in, that's your group there, and we once again regenerate the H+ that we initially put on to make this reaction go. So it's an acid catalyzed, not an acid reactant, but an acid catalyzed SN1 with rearrangement. This is really weird at first. So I'm assuming you're looking at this and going, things just flying by. What the heck just happened? So be very systematic in what you're looking at. So take the kind of notes that you'll remember. No, don't just copy what's written here, but write the things that help you. So in the first one, OH is a bad leaving group, but if I protonate it and make water, water's a good leaving group. So I'm going to make note of that. And that's going to be pretty important. Water is a good leaving group. Okay. Number 2, when you get a secondary carbocation, look at the neighboring 2 carbons and see if it can move over and become tertiary. No, yes. So that one will shift over, get a hydride shift because again, it's a hydride moving over. It goes from a secondary carbocation with 2 to a tertiary carbocation with 3. Now it's stable, not going to rearrange. So by the time the thiol comes in, the thiol comes in, we're going to find that when it attacks, it's going to attack the tertiary because it had time to rearrange, and then it's going to deprotonate to become neutral again. So sorry that plus charge has been blocked out by the arrow, but those electrons coming in finishes the task. So afterwards, the things we have to worry about would be the fact you get a racemic mixture. Maybe, so we have to consider that. So is this chiral center here RS? Well, let's figure it out. Priority number 1 is a sulfur, 2 is a long chain, 3 and 3, oops, CH3s are the same thing, so therefore, not a chiral center. So racemic mixture, it's achiral. So it can't be racemic. And then the second question, what's a rearrangement? You bet. So you ended up taking a leaving group off of this carbon and having the nucleophile ultimately on that carbon. Okay, very, very complicated multi-step process that is really daunting at first, but you'll pick it up as you go. Rearrangement will only happen if you can increase the quality, the stability of the carbocation. And because rearrangement is so fast, it's easier to move around your own couch than somebody to come in from across the room and sit on it. Rearrangement always needs to be considered. If there's rearrangement can improve it, it will happen. Then you'll get your substitution. Okay, so is it fast or slow? Well, you're waiting around for something to leave, so it's slow. And you're waiting for all these steps. Very slow reaction, relatively speaking. This is all a relative speed game. So the rate for an SN1 depends only on the electrophile, does not depend on the nucleophile at all. So this had no bearing. That thiol had no bearing on how quickly reaction occurred. Okay, that kind of ties off SN1 with a special case and puts us into a scenario where we want to start comparing the two of them. We want to compare it. Why would it be SN1? Why would it be SN2? And so things to consider that we mentioned. In the beginning, before features of the reactants we need to consider, if it's a very crowded electrophile, then it has to wait till it leaves. If it's very uncrowded, then it can come in and attack. So primary will definitely be SN2. Tertiary will definitely be SN1. Secondary can go either way, which makes it a little more challenging. We next look at the combination of nucleophile and electrophile. This nucleophile is coming in, so a good nucleophile and an average leaving group will help. For this one, a poor nucleophile is fine, but you have to have a good leaving group, something that wants to come off. So you have to have a nucleophile for an SN2, you have to have a good leaving group for an SN1. And last but not least, the solvent. So again, mention that if it's polar and aprotic, non-hydrogen bonding, it doesn't hinder the nucleophile very much, but it helps with the charge, the dipole you get in the transition state, helps it to be stabilized so the reaction can occur. So you want something polar. So again, an ether, a ketone, DMSO, these are solvents that will pop up as we talk more and more about the specifics of the reactions. Protic, methanol, ethanol, amines to some extent, but they're a little too reactive, so don't make good for a good solvent. Water, again, it can be too reactive, but anything that can hydrogen bond, H on an O, H on an N. Technically, H on an F can, but HF, hydrofluoric acid, is not a very good solvent. Okay, so I want to compare reaction rates based on the numbers. So there's an excellent table from the book I want to mention, and that is the nucleophile is going to attack methyl iodide. So absolutely no steric hindrance at all, 3 H's. So this is even better than primary. So this is by all means going to be an SN2. The nucleophile, drawn generically, we're going to actually give a series of different nucleophiles coming in and displacing iodide. So the nucleophile is going to come in and kick out the iodide. So want to consider halogen nucleophiles. So the table in the very beginning that we had of this chapter, we mentioned iodide was a really good nucleophile, bromine pretty good, chlorine's okay, and they put F on the cusp of good, bad. I'd mentioned something at the time that that list is, I mean, not the best because conditions make a difference. Like ammonia can move up and down that list. So can fluorine, and that's kind of what this study proved. So in this study, they chose 2 different solvents. The impact of peer pressure. So consider yourself to be a famous singer. You have this entourage, they cling to you. Whenever you get done your concert, you just try to move around and you can't because everybody's clinging to you. So it would be no surprise if like TMZ caught you on film, caught you on audio, crying out, "I feel like a fluoride in a protic solvent." I feel like a fluoride in a protic solvent. Totally reasonable to cry out to the world. I mean, stars do this all the time when they're frustrated and they're in their little bubble. They cry out these crazy statements. And this is a very valid chemistry statement. I feel like a fluoride in a protic solvent where the solvent is clinging to you, so you can't move around, so you're very, very slow. Well, hydrogen bonding is significant in F, but it gets the interaction of water with these other ones far, far less. So notice this is almost a factor of 100 in this one, like 67 or so. This factor 25, factor 43. So as they interact with water less and less, and as they interact with methanol less and less, as they interact with a protic solvent less and less, they're free to move around. So iodine, perfect. You'll notice a few stars in the chart, so just want to point out what those are. If iodine is your leaving group and your nucleophile, how the heck do you measure a rate? And what you do is you make one of them radio-labeled. You want to make them one of a specific nucleus. And then everything is relative to methyl iodide and bromide. So they're using this as the one value, meaning bromine coming in, iodide going out, and saying that's a standard rate. So this one's 43 times faster, 0.04 times as fast, and so forth. Okay, instead of methanol, a protic solvent, we use DMP. So this is DMF, excuse me, sorry. Weird screen at the moment. So protic apolar solvent, so aprotic solvent, so it still has a dipole moment. It can facilitate delta plus, delta minus, but aprotic means it doesn't hydrogen bond. So in this case, the DMF is not going to bind to the fluorine. So again, picture yourself performing here at Pepperdine. You're a world famous singer. Thousands of people come to watch you sing. They cling on to you. Everybody wants to be your friend. But here at Pepperdine, you're completely unknown because, well, you're at Pepperdine. They don't know you. So you're able to freely move around the campus without an entourage clinging to you, which means because you're small and able to get around, you can move faster than the bulky iodide, the bulky bromine, the somewhat bulky chloride. So notice everything's sped up. Number one, the solvent isn't hindering you to move around. So you went from being the slowest by a very large amount, I should say, to being the fastest. Now, fastest by just a little bit, but suddenly what was the worst nucleophile is now the best, was the best has now become the worst. So that list of how good the nucleophiles are, I'm not going to stick to it too seriously because conditions affect everything. And so it's a good starting point, but note that that whole thing, your environment, your entourage, those that cling to you will impact how quickly you react. With nobody clinging to you, move around quickly, reactions are fast. So SN2 in a aprotic solvent is going to be very fast. SN2 in a protic solvent is hindered. So aprotic solvent definitely helps. They put the factor of how much it increases. I don't know if that's a good thing, but I mean, there it is in the table. I'm more interested in just the fact that F is the slowest in one, fastest in the other. Entourage slows you down. No entourage, no slowing down. Again, also want to reiterate that the rate depends on the comparison of iodine, one isotope compared to the other in the reaction, and that overall this process has to do with the solvent effects. So SN2 prefers an aprotic, non-hydrogen bonding solvent, whereas SN1, a protic solvent, will help bind the leaving group and pull it off. It also stabilizes the carbocation during the reaction. So made a big ordeal about one of them having 5 things on there, 2 of them monocheeking. Big ordeal about this one being a 3-ligand planar intermediate with sp2 hybridization that can be attacked from either side. The bond angle drops to less than 109.5, so it ends up being 90 between the nucleophile and the other substituents on there. So it gets awfully crowded. And then in SN1, it goes from 109.5 up to about 120 because the sterics of those crowded groups helps to push the leaving group off, helps facilitate it. So for instance, in the SN2, small, so it comes in attacks, but for a brief moment, you have a monocheeker on one side, monocheeker on the other, so 5 things attached. And hopefully this works well. Couple things to make note of. Notice I put a 2 and a 1, a deuterium and a hydrogen. So for chiral centers, we go by atomic number, but there was a little caveat. This is the one I mentioned briefly, and that was when you have the exact same atom, a Z of 1, nothing else attached, and it doesn't matter, nothing else attached or everything attached, irrelevant. It's just the isotope effect. The deuterium is higher priority than the hydrogen. It's on here just to get some sort of preference. So we have a chiral center of 1, 2, 3. So it starts out at S. In the end, it's now 1, 2, 3, H and back, so R. So we did in fact get an S to an R, so we got inversion. And we had this 5-centered intermediate. SN1, again, crowded. So I'm doing the same thing, but now with the chiral center. So chirality is 1, 2, 3. So again, starting with an S, goes to a tetrahedral, a planar intermediate. So no chirality, no center. It can attack from either side. So if it attacks from the left, you get one chiral center. If it attacks from the right, you get the other chiral center. Because there's no other chiral center in the molecule, there's no preference or favoritism, so you get a racemic product mixture. You get R and S. So here we have our S, here we have our R. Okay, good summary of what we get in the end. So your job, know this table, not just what fits in the box, but know it ideologically. So you get inversion, R to S or S to R, if the priorities don't get jacked up. Racemic mixture and possibly rearrangement, hence the question mark. It's second order coming all the way back to the 2. So I told you it was option 2 in the niceness, but really the 2 stands for second order, meaning it depends on 2 molecules in its rate determining step. SN1 only depends on 1, the electrophile. So the nucleophile influences the rate. It does not in an SN1. And then last but not least, concerted, like a concert, like you're famous at because you're an incredible singer, everybody's performing together. So concerted reaction, everything happens in 1 step. Everything's going on simultaneously, very fast. 2-step, you have to wait. Somebody has to lead before something comes on. So SN1s are slower reactions. That means there are 1, 2, 3, 4, 5, 6, 7, 8 different ways I can compare these 2 reactions, and I will. So the graphs, note that a concerted reaction starts with reactants, goes through transition states, and spits out a product. In an SN1, you go through a transition state, but then form an intermediate carbocation. Then it rehybridizes again, and the nucleophile comes in, and you get a product. So hopefully this seems okay. So I'm not going to belabor this other than SN1 or SN1, 2 steps, SN2, 1 step. So it's not named for the number of steps. It's named for the number of things that matter. Nucleophile and electrophile both matter in an SN2. Just the electrophile matters in an SN1. Oh my gosh, it's happy time. You can tell by the smiling faces and the I'm so happy and I love happy time statements. So practice makes you happy, so let's do some. Blah, 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 blah. I like reading questions to you, so hopefully that clears it up and you understand. Every now and then you're going to come across a question like this, and this is where a good vocabulary will save you. Again, I've mentioned this, but I want to reiterate this every chance I get. Big Bird of Sesame Street fame is the greatest multiple choice test taker that has ever waddled the planet. And just to explain why this is, he wrote a song specifically for this, that for your OChem class, in fact, where what he's saying was one of these things is not like the other, one of these things is not like the rest, therefore pick it on your next OChem test. I'm pretty sure those are the exact lyrics. You as a professional singer might know more than I, and you might actually even performed it live. But I'm just going to focus on the one of these things is not like the others. So yes, Sesame Street has paid dividends. So rearrangements is observed. Now that was a carbocation phenomenon which happens with SN1. The rate does not increase as nucleophile is added. Okay, it only depends on one thing, the electrophile, not nucleophile. That's an SN1 feature. Optical activity is lost over the course of the reaction. Well, SN2, you got inversion, so optical activity goes from, let's say, positive to negative, D to L, whatever they want to call it, but you still have it, it's not lost. Whereas when in SN1, you get a racemic mixture. Racemic mixture would be part S, part R, so therefore it'd be half and half. You have no optical activity. So that sounds like an SN1 feature. And then specific rotation changes its sign, meaning the nucleophile comes in from left, it used to be on the right. So you go from something that has the higher priority on the right side to the left side. It's going to go from a positive rotation negative or negative to positive. That is an SN2 backside attack phenomenon. So without knowing the question, you have to decide which of these is different Well, one of the things not like the other is the SN2 is different than all the SN1. So pick the one that is not like the other. Again, this is not going to be the best test approach, but the more you know about the definitions, the easier questions like this will be when you just don't understand what it's asking. Okay, so this one, totally different question. La-di-da-di, 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 blah, blah, yippee. Again, very in-depth, articulate question, very, I don't know, very cutting edge in science, but I don't know what it's saying. So Big Bird would tell me one of these things is not like the others. It is preferred with a primary electrophile. So if I remember right, smaller was SN2 because you come in, you don't have to wait. SN1, you have to wait around. That's when it's really crowded. So this is an SN2 feature. No intermediate. Ah, that's right. SN2 only had a transition state. As it comes in, it's pushing another group off. So there is no intermediate. It just happens in one step. Polar aprotic. So again, that's really key. Protic solvents help pull leaving groups off and stabilize carbocations. Aprotic prevent that from happening and allow the reaction to occur less hindered. So SN2 and hydride shifts, or if it was a methyl group or an ethyl group or something like that, we call it an alkyl shift. Those can only occur when you have a carbocation, so only when you have rearrangement, SN1 feature. So one of these things is not like the other once again. So SN2 features all across, except for one SN1 feature. Choice D is the one that is not like the other. So I'm picking on these sorts of questions a little too much. So let me go to a real question, but hopefully you get that basic gist. The more you know that table, all the different factors involved, the more you can start making those sorts of decisions. Okay, this question, which change to the reaction result in a change in the nucleophilic substitution mechanism by which it proceeds? So for me, the hardest part of this one is asking or figuring out what are they asking. So what change in the reaction would make it change by a different mechanism? Meaning, what would make it, if it was SN2, turn into SN1? Or what would make it go from SN1 to SN2? Okay, so what are the things that would matter? If I change the solvent from methanol to acetone for nuclear solution of a tertiary bromide. So the key thing there, tertiary. The fact that it's tertiary means it can only go by an SN1 mechanism. No matter what you do with the solvent, from methanol to acetone, it's just going to slow it down and make it even slower. But because it's tertiary, it still is going to go by an SN1 mechanism. So choice A, tertiary electrophile, equals SN1. Changing the solvent is irrelevant. It's not going to change that mechanism. Okay. B, change the nucleophile from this to this in THF, ether. Okay, that's kind of interesting. Secondary. Ooh, secondary is going to be interesting. I'm going to come to secondary last because I can't immediately eliminate it. Same thing here. So secondary, because those are going to be a little bit trickier, I'm going to do those last. Primary, so change the alkyl halide from one with a higher bond dissociation energy to one with a lower bond dissociation energy for the nucleophilic substitution of primary. So primary, no matter what, is going to be an SN2 reaction. So having a higher bond association energy means a weaker or worse leaving group to one with a lower bond association energy, weaker bond, so easier to break, so a better leaving group. So if I go from a worse leaving group to a better leaving group, it still doesn't matter. I have a primary. Primary is going to go by an SN2 mechanism, independent of the leaving group. Okay, so now we're down to the two up here. If I change a nucleophile from a good nucleophile to a good nucleophile in an aprotic solvent, from an aprotic solvent, I didn't change anything. So secondary electrophile could go either way, and I changed from good nucleophiles in aprotic solvents. Both are going to stay SN2 because they're both good nucleophiles and aprotic solvents. I sure hope C is right. Changing from a good nucleophile to a bad nucleophile, ooh, that could be useful. It could be SN1 or SN2 because it's secondary, but because the nucleophile is good, it's going to favor coming in first. But when I switch to a worse nucleophile, I'm going to find that it becomes less of a nucleophile, so it's going to be hindered, it's not going to be involved in the reaction, and therefore it's not going to go by SN2. It's going to wait till it leaves and go by SN1. So this is my best answer where you went from a good nucleophile to a bad nucleophile with a secondary. So secondary could be either way. You give it conditions that favored SN2, turn into conditions that favor SN1. This is a really really tough question. So it's one of those, it's worth doing this multiple times to get a feel for this. But the key thing, look for tertiary, secondary, primary before you do anything else. Tertiary, SN1, primary, SN2, secondary, dang it, more work. Then consider good nucleophile, aprotic solvent, SN2, good nucleophile, aprotic solvent, SN2, good nucleophile, aprotic solvent, SN2, poor nucleophile, SN1. So hopefully this helps. And again, if you're going by the list, this one is barely on the side of good according to that line. But I'm going to go with the fact this is a much better nucleophile because it's negative compared to this. Okay. Alcohols as electrophiles. This is going to actually get way ahead of ourselves because although this is chapter 7, this also fits into chapter 12 when we deal with alcohols. But still want to just look at this. We said that OH is a terrible leaving group, doesn't come off. So there's different ways you can turn it into a better leaving group. One of the things we did is we protonated it in that one example and turned it into water. So you'll note if I have a compound that is R to begin with, or S, I'm sorry, I went with S on this one. So let's say we have this. I want to make it S, so I'm going to make it a methyl, the lowest priority alkyl group. And H. And then what I'm going to do then is I'm going to get rid of my first R and make it, no, I'll just leave it as R, sorry. It's going to make it a bigger group, but I have my priority 1, 2, 3, counterclockwise, H's and back, so that is an S alcohol. When I protonate onto water, I'm going to make that plus, it is still priority 1, 2, 3, it's still S, is what they're saying. Okay, if in the next step, I'm going to turn it into something called a tosyl chloride. The H gets taken off, and instead it gets this sulfur compound. I'm just going to put TOS for now. I'll draw what it is in a future question. We'll do it. I just don't have the space here. But it's basically a sulfate, O adding onto a sulfate with a benzene ring. But that bulky group goes on, but notice the chirality of this carbon is still O, R, and CH3 for priority, still S. So you end up getting this compound with S chirality. There's also one where the same thing, but instead of having the sulfate with a benzene ring, it's just a methyl group. So one of the issues you sometimes run into is that, actually, let me see if I can get rid of it this way. Sorry, there we go. So one of the things you run into is if the group gets too bulky or too small, it impacts the reaction. And so if you can afford the bulk or you need the bulk, tosylate. If you don't need the bulk, you can go with mesylate. It's just a little bit smaller. Same impact, essentially does the same thing. I probably won't make a big difference or a big deal distinguishing them. In a different category, now we're starting to get into something a little bit trickier. So let me get rid of my mesyl group and tell you what happens with this one. PBr3 is a phosphorus with 3 bromines. And before I do anything, I want you to ask yourself, is phosphate something you've ever heard of? Does phosphorus bind oxygen? The answer is definitely yes. So there's a strong interaction between oxygen and phosphorus. So what happens is this alcohol can attack the phosphorus, kick a bromine out. In fact, 3 different alcohols can attack that phosphorus and kick bromines out. Now, what happens after that is you now have this species where you have the O connected to a phosphate. And I'm just going to put a circle around it to represent. In fact, why don't I color coordinate it so I stay with this yellow, but phosphate group. The same chirality as before, an R. And so what can happen is the Br, which is negative, can come in and attack via an SN2, meaning this can only work on a secondary or a primary carbon to get this substitution. But because it's backside attack, if it starts out with S chirality, priority 1 used to be the O, priority 1 is now the bromine. So if it started out with S, the bromine replaces it, and you end up with the R. So in this case, the final product you're going to get will be bromine bonded as such to the carbon, which you now have the R up here, the H over here, and the CH3 here. So you now have the opposite chirality. So whereas this used to be 1, 2, 3, S, this is now 1, 2, 3, R. So you end up going from S chirality to R chirality. Okay, going to get rid of all this and add in the last one. SOCl2, again, like sulfate, oxygen is going to want to bind sulfur. So much like O attacked phosphorus, like it does in a phosphate, O attacks sulfate. When it attacks SOCl2, it cooks out the Cl minus. Just like the Br can come in and attack the carbon to kick out the O, Cl can come in from the backside. So this is an SN2. So first, it's binding the O, and then it's going to do an SN2. PBr3, same story, SN2, which is why you get inversion. Why do I care? Well, the reason I care is because sometimes the synthesis I want to do, I'm really interested in getting a very pure enantiomer. So if I do an SN1, I get 50-50, I get a racemic mixture, it's not so good. So SN2 is clearly better, but I have to figure out what I want. So if I want to go from an R alcohol to an R product, or an S alcohol to an S product, I have to figure out my inversion. So because we're doing S, let me stick with that. So here's my S alcohol. If I use PBr3, it's going to turn into an R, but Br is a good leaving group. So if I do another SN2, so successive or consecutive SN2 reactions, the first one turns S to R, and then the next one is going to turn R back into S. So if my goal is to get an S center, then double inversion, going from S to R, then back to S, will work. If, however, let's say my goal is to get an R group. Well, OH is a terrible leaving group, so I got to do something to it, but I don't want to do anything to change chirality because I want it to invert in the second step. So I'm going to use one of these three: tosylate it, protonate it, mesylate it. So if I added tosyl chloride, again, no inversion, so it starts with S, turns into S, and then when I treat it with KCN, same thing as before, it's now going to come in from the backside and give me a product with R chirality. So if you were trying to do a chiral-specific synthesis, and alcohol is your starting group, you need to figure out what you're going to do for your double inversion. Do I get one inversion in the second one and keep the same chirality? Or do I do non-chiral conversion into a better leaving group followed by an inversion of an SN2 and get overall inversion from starting chirality S in this case to the final one, R in that case? So hopefully this seems okay. So making alcohol a better leaving group can be done in many ways, and then also pay attention to the stereospecificity of it. You cannot make a tertiary a better leaving group using PBr3 SOCl2 because those are SN2 reactions. So we're all done, at least for now, and we'll continue on. So this is just an overview of how we compare the SN1, SN2. So we'll be working on that in pretty good detail. So I will see you at the next podcast. So have a great day and see you soon.